Friends, welcome to this lesson on programmable timer and counter. Many industrial control applications require the generation of precise time delays. An example would be the sequence timer used in a process control application. Such a sequence timer would require to switch on and off a motor or open and close a valve at specified time delays. Even a simple application such as a traffic light involves switching on and off lamps at regular time interval. Normally, such time delays are produced using mechanical timers. Sometimes electronic timers are also used, which are done out of discrete logical gates. A microprocessor-based system can also be used to generate these time delays under software control. Certain other industrial control applications involve counting certain events. For example, the number of bottles moving in a bottle filling plant need to be counted, or the number of medicine tablets that are filled into a bottle need to be counted. These counting can be done under software control using a microprocessor-based system. So these time delays and counting can be done under the direct control of CPU. However, this places heavy demand on the time of the CPU. A better approach would be to use a dedicated device for this counting and time delay generation. The Intel 8253 is such a device which can be used for counting and generating time delays. Intel 8253 is to be used with 8085 CPU. In this lesson, let us learn the features of 8253.
The two functional blocks of the device are the counter timer section, the microprocessor interface section. The device has three independent counter timers: counter 0, counter 1, and counter 2. Each is a 16-bit down counter. Each of them can be operated independent of the others. Each counter has a clock input and gate input and one output. The gate input enables the counting process. The counting may be started using this gate signal. Thus, the starting of counting may be synchronized with an external event. The counter indicates the completion of the counting process through the out signal. Each counter can give 6 different types of output. The 8 data lines D0 to D7 are connected to the data bus of the microcomputer. Each counter presents a logical register to the CPU. The device presents a total of 4 logical registers to the CPU, 1 for each counter and 1 more for the control. The A0 and A1 lines are connected to the A0 and A1 lines of the address bus. The CS bar pin enables the device. The read bar and write bar signals allow the CPU to read and write into the 4 logical registers. The device can be operated in I/O mapped I/O mode or memory mapped I/O mode. To operate in I/O mapped I/O mode, the read bar and write bar signals are connected to the I/O read bar and I/O write bar control signals of the bus. The address decoder selects the device for I/O addresses 10, 11, 12 and 13H. 8253 is a fully programmable device. It is programmed to select the counter mode, to initialize the counter and to read the count value. The first step in programming the device is to load the control word into control word register. It is followed by loading a 16-bit count value into the selected counter. The D7 and D6 bits are used to select any one of the three counters. D7 and D6 together represent the number of the counter in binary notation. For example, to select the counter number 2, D7 is 1 and D6 is 0. The D5 and D4 bits select either reading or loading the count value. When both are 0, reading of the count value is enabled. When D4 alone is 1, the lower byte of the count value alone is to be loaded. When D5 alone is 1, the higher byte of the count value is to be loaded. When D5 and D4 are 1, the lower byte is loaded first, followed by the higher byte.
Before learning other bits of the control word, let us discuss the type of output produced by a counter. Each counter is capable of producing different types of output. For instance, the counters may be used to produce a specified time delay, a square wave of given frequency, a monoshot pulse of given width. Each output is defined by an operational mode. The 8253 features 6 different operational modes. Let us go over to the graphics to learn the details of remaining bits of the control word.
The bits D3, D2 and D1 are used to select the operating mode. The 3 bits represent the binary value of the mode that is to be selected. The counters may be made to count in binary or BCD format. The D0 bit selects this.
The 8253 features 6 modes of operation. Each mode basically implements down counting. When the counting is completed, an output is provided. The 6 different output formats are provided to meet different applications. Further, the counting may be initialized by the software or the hardware. This increases the flexibility. For certain modes, the loading of the count value itself triggers the counting. Certain other modes require an additional hardware pulse to start the counting. Thus, the software or hardware triggering and the output format completely define a mode. Let us go over to the graphics to learn further details about the modes.
This mode is a simple down counter mode. The first step is to load the control word into the control word register. The output of the selected counter goes low immediately. Then the count value loaded into the count register. The counting begins immediately. When the number of pulses counted equals the count value, the output goes high. This mode can be used to generate specified time delays. The output signal may be used to interrupt the CPU. The control word and the count value are loaded into the device registers. This mode needs a trigger signal given at the gate input, and the counter starts counting. At the next falling edge of clock, the output goes low. When the number of pulses counted reaches the count value, the output goes high. The counter can be used as a triggered mono shot of desired width. The mono shot is re-triggerable. That is, a trigger at the gate starts the counting process. Before termination of the count, if another trigger appears at the gate, the counting starts again. Change in count value is allowed when the count is in progress. However, the change becomes effective only after the next trigger.
Friends, we have learned the details of mode 0 and mode 1. Now we will see a demonstration of using the counter in mode 1, that is, to use the counter as a mono shot. The clock input for the counter is generated by this switch. The status of the clock is visually displayed by this yellow LED. The output of the counter is displayed by this red LED. The gate signal is generated by this switch. These two switches are debounced by the circuitry provided here. The signals are connected to the gate using this ribbon cable through this connector of the trainer kit. A program is loaded in the user area of the trainer kit. The program sets the counter 2 for mode 1 operation and for BCD count. Now let us examine the content of the program. The program starts from the address 8C00. 3E is the opcode for the move immediate A instruction. B3 is the control word to set counter 2 in mode 1 and for BCD count. D3 is the opcode for the out instruction. 13 is the address of the control word register. 3E is again move immediate into A instruction. 06 is the LSB of the count value. D3 is out instruction. 12 is the address of the count register. 3 is again move immediate A. 00 is the MSB of the count value. D3 puts it out onto the count register, and finally 76 is the halt instruction. Now let us execute the program. First, I am disabling the gate. Now I am giving the clock pulses 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means even after 6 clock pulses the output is not coming high. That is because the gate is disabled. Now I am enabling the gate. Now I am giving the clock pulses 1, 2, 3, 4, 5, 6. After exactly 6 clock pulses, the output has become high. Thus, the counter 2 is working as a monoshot.
The mode word and count value are loaded into the register. A high level at the gate starts the counting. After counting pulses equal to count value -1, the counter gives out a low going pulse for 1 clock width at the output pin. Output of this pulse is repeated every time the count reaches the count value -1. Change in count value is allowed when the count is in progress. However, the change becomes effective only after the next output pulse. This mode generates pulses occurring at a rate specified by the count value. The mode word and the count value are loaded. A high level at the gate starts the counting. The output remains high for exactly half of the count value. It remains low for the rest of the count value. Thus, this mode generates a square wave of periods specified by the count value. Any change in count value becomes effective after the present count is over. When the mode word is loaded, the output goes high. The loading of the count value starts the counting. When the count reaches the count value, output goes low for 1 clock period, then goes high again. The gate signal may be made to disable the counting. When counting is on, if gate is made low, the clock pulses are ignored and thus counting stops. The counting resumes when the gate is made high. Any change in count value becomes effective after the present count is over. The mode word and count value are loaded. The counting is started by the gate signal, that is, by hardware. A low-level pulse of 1 clock duration is generated when the count reaches the count value. The counter is re-triggerable. That is, when the counting is on, if gate is made low, the counting is made to start from the beginning.
As a programming example, let us consider the problem of dividing a 10 kHz clock by 10 to provide a 1 kHz square wave output.
To select counter number 2, loading a 16-bit count, mode 3 operation and BCD count, the control word format works out to 10110111, that is B7H. This program segment will load the control word B7H into the control word register at address 13H. To load the divisor 10 into the counter 2, the 16-bit value in hex is 0010H. This program segment will load the value 10 into the counter 2. The address of the counter 2 is 12H. This program will divide the clock input by 10 and the output will be the square wave output.
Friends, we have seen the description of modes 0, 1, 2 and 3. Now we will view a demonstration which implements mode 3. The clock output of the function generator is given as the clock input to the 8253 of the microprocessor trainer kit. The output of 8253 is connected to the oscilloscope. The clock input is also connected to another channel of the oscilloscope so that clock and output of 8253 can be viewed simultaneously. The counter 2 of 8253 is set for mode 3 and BCD count. The count value is set as 6. Now I am going to execute a small program which loads the control word and the count value into the registers. Now the clock input and the output of 8253 can be seen on the oscilloscope. The upper trace shows the clock input to the counter 2 of 8253. The lower trace shows the output of counter 2. It can be seen that for every 6 clock pulses, a complete square pulse is produced at the output. Thus, the clock signals are divided by 6 at the output. Now I am going to change the count value as 10 so that the clock pulses are divided by 10. Now it can be seen that only for every 10 clock pulses a complete cycle at the output is produced. When the counting is going on, the contents of the counter may be read. The device has internal arrangement to latch the count value. The intermediate count value can be used to change some parameter of the process. For example, if 100 pieces of toffee have to be packed in a bottle, after every 25 pieces, the color of the toffee may be changed. The control word has provision for reading while counting.
To read counter number 0 while counting, the control word would be 0000 X X X X. X denotes either 0 or 1. Bits D7 and D6 represent the counter number. The 00 on bits D5 and D4 represent latching operation. The out13H instruction loads the control word into the control register. The in10H instructions load the count value into the BC register pair.
Let us review what we have learned in this lesson. The 8253 is a programmable counter timer device. It has 3 independent counters. Each counter has 6 operational modes. The counting can be triggered under software or hardware control. The contents of the counter can be read when the counting is going on. Thus, the 8253 implements efficiently the counting and timing requirements of a microcomputer. So, until we meet again, goodbye.